Okay. Good morning, everybody. I apologize up front for my scratchy voice. And if you can't hear me at the back, please shout. But we've been in the 80s down in North Carolina, and the pollen's been rampant, and I'm suffering from a major overdose of allergies. So with that, please. Okay. Did we lose? People? My topic that I chose for this lecture series was the Green Steel Revolution. And I'm sure we're going to have to change the title moving forward. But as Dr. Chen said, the Elliott lecture, it was put together in 1990 to honor Dr. John Frank Elliott. He was a late professor at MIT, and he had many significant aero and chemical process metallurgy. What's that? I need a pointer too. Okay. He's authored many, the thermodynamics of steelmaking, and he's also worked throughout his career at U.S. Steel Development Research Labs, Inland Steel, MIT, and the Navy. But the aim of this Elliott lectureship is to acquaint students and engineers and public, where appropriate, about chemical process metallurgy and its applications moving forward in the future, and the exciting opportunities that exist for you students to come into the industry, and the hope that you will follow an inspiring career. Back in 1972, he gave a Journal of Metals paper, and he said at that time that electricity will become more important as an energy source in the future. However, it was unlikely he was looking at the problems of CO2 and hydrogen at that particular time. I'm honored to have been chosen the 2024 Elliott, and for those students who may be debating their future, please understand that I've been in this industry for 50-odd years, and I failed my chemistry. Almost failed my chem met, and I've still been doing this for 50 years. If you have a passion, follow it, regardless of your academic achievements early on. So why a green steel revolution? I'm defining green steel revolution as net zero emissions steelmaking using fossil-free energy sources. And the zero emissions, as I'll show you in the iron making, is crucial for the greenhouse gas mitigation. Currently, we're not competitive with the fossil-based fuels. And for those taking notes, I'm going to give a copy of this to Prof. I saw you with your pen. There's a lot of information in here that's way too intense to complete throughout the time of this lecture. So I'm going to give her a copy that can be circulated, or if you want, you just ask me for a copy. The world's currently missing out on, which is now it's on. Okay. You can see on the chart at the right, that's not doing it. Can I go get mine?
Yeah, if you want.
I want the pointer.
Yeah, you have a pointer. Oh, you want the laser pointer?
Yeah, this one. I'll do this. The bottom right-hand chart is showing where the two greens cross where we are currently. About 41.5 in 2022 was where we were. We're way ahead of the 1.5 degree mitigation. And in fact, we had 37.4 gigatons of CO2 in 2024. It was a 0.8% over 2023. And why the green steel revolution? Well, basically, the Europeans started this in 2015 when they said that the future was going to be the conversion of 800-year-old blast furnace technology based on carbon and the BOFs moving forward into a 60-year-old technology, which is electric arc furnace steelmaking. But there would be major changes to the modus operandi. There would be carbon-free electricity, hydrogen direct reduced iron as a charge, and we'd have to have green carbon, excuse me, and consumables going into the furnace also. There's been increasing disinterest, as I'm sure you've all seen in the news over the past couple of months, and probably the last couple of years, technically. And it's motivating out-of-the-box thinking for new technologies that can be applied. And I will look at some of those as we go through some of the major ones. This has been attempted back in the 80s and 90s without too much success, so we're hopefully moving forward. I'm not going through this chart, but basically the current steelmaking technologies are blast furnace, smelt reduction, the direct reduction, and electric furnace steelmaking, and this actually represents 100% scrap. And as you can see from the bottom, it's still not working. No. On the bottom of the chart, there's iron making as the first set of figures, and as you move from left to right on the blast furnace to scrap, you can see that the the actual tons of CO2 per ton of steel is going down significantly from 2.2, which is probably the worst in the world. Thank you. To 0.38 when you get to the 100% EAF steel making. And that will actually come down further, as I will show you as we move forward. Carbon dependence is both in the blast furnace and the EAFs. You can see from all of the equations here on the right-hand side that there's a lot of carbon interaction in the blast furnace. And of course, we need coke in the blast furnace to actually hold the charge up. On the EAF side, there's equally a lot of carbon reactions. I'm not going to go through them here, but one of the big issues for the EAF, beneficial issues, is the foamy slag that's formed with the carbon-oxygen reactions. This reduces a lot of the arc noise. It also helps with the chemical reaction. And basically, because of the surface area, it allows a lot of reactions to occur. And then we have stirring from the CO2 that's evolving through the blast. That's me. Sorry. I need two hands. It is. I'll just use this for that. Now, the Paris Accord is looking for 0.2 tons of CO2 per ton of steel by 2050. Right now, we're nowhere near that. We're at about 0.7 average throughout the world. The major emissions, as you can see, are coming from the blast furnace, basically. Coke ovens, the EAFs is a third, sinter plant, and then the BOS. The chart down here at the bottom basically shows all of the countries that produce steel in excess of 10 million tons a year. The red is the blast furnace BOF route. The green is the EAF route. And as you can see, China on the left-hand side here is 54% of steel. And about 90% of that is coming from the blast furnace BOF, which is why they've got 29% of the CO2 generation for the world. India, on the other hand, which is the second highest producer, is 56, 57% EAFs, and they were 58% in 2021. Just as an interesting fact, the Canadian fires that happened back in 2023 contributed 647 million tons of CO2 to the atmosphere, and that put them in fourth place behind China, India, and the United States. So in the International Energy Authority's vision in 2070, and the green challenges is what I'll look at next. The net zero conversion is to 95% hydrogen DRI EAFs. It's technically feasible, though it's fraught with challenges, and I'm going to go through about 9 of those challenges. They are exorbitant in terms of cost, and they are driving the other technologies to be developed, some of which are still at TRL3 and some are now up at TRL7, and some of them have achieved that in less than 7 years. So this is really the most exciting era, kind of like Professor Chen's innovative center here. It really is an exciting time to be in the industry. Now, green challenge number 1 is what I call build rates. I don't think any of their projections are achievable. It's predicated on hydrogen, on renewable energy and carbon, and better qualified or quantified scrap. Just as an example, from 1970 through to 2020, the average DRI plant construction was 2 million tons a year. By 2050, the IEA is proposing that we're going to need 411 million tons of DRI, of which 213 million of that will be hydrogen DRI. That's going to require 11.5 million tons of hydrogen, 692 terawatts of energy, which is going to require 1,240 20 megawatt pens for the hydrogen, and then it's going to be 810 electric arc furnaces required. Additionally, if you're having zero carbon DRI going into the arc furnaces, you're going to need another 370 terawatts per year of power to overcome that. There's also supply chain challenges which have come to the fore since our COVID days. Currently, transformers are taking 106 weeks for delivery, and the costs are sometimes as high as 85% more than they were pre-COVID. Challenge number 2 is sourcing the green hydrogen. It's expensive. There's an inadequate supply. The right-hand side here shows what Lindy has predicted for each area, 65 ton a day of hydrogen for the blast furnaces alone. In 2023, this is the hydrogen map. It's a great source, and there's another one further on that I will show you. But it shows you all of the world's low carbon hydrogen projects that are ongoing, blue and green. In 2023, we had 1,040 projects ongoing. There's $110 billion of front-end engineering development costs. And only 25% of that have gone as far as final investment decision, which is 7% investment. One of the issues we have with hydrogen is its production efficiency, currently 27 to 65% more than the stoichiometric requirement. There are a couple of new developments going on. There's an 8 kilowatt hour per kilogram plasmalysis jet loop, where they're removing ammonia from wastewater and manure and creating hydrogen at a fairly low cost in terms of power. There's NEXT, which is an RMIT in Australia. They're using sound wave integration into the standard electrolysis systems, which will allow it to produce a huge amount more, 14 times more production than the current electrolysis. And there's a new one, Utility H2 Gen, which has been in demonstration on Cleveland Lake Erie works recently, and the first, I'll get into a little bit of that further on. The other issue is the cost of the electrolyzer capex. It needs to be reduced 70% before it becomes viable. Currently standing at about $1,000 to $1,750 per kilowatt. It needs to come down to about $300 if we're going to move forward. Third challenge is sourcing the green energy, basically. Excuse me. We actually use 8% of the world's energy, and at 0.3 to 1 kilograms of CO2 per kilowatt hour, there's a lot of CO2 that can be generated. We're going to need 1,437 terawatts by 2050. It's a $2 trillion investment. And this chart on the right-hand side here shows all of the different modes of production of energy. And it's come from this global energy monitor and project tracker. Basically, there's not enough hydrogen at the right price. We need at least a 50% reduction, if not more. 2022 renewable energy was about 29% of our energy sources, and China was leading the way. The capacity adds that have been put on, 2023 was about 0.5 terawatt, and in 2024 was 0.6 of a terawatt. Hydrogen was predicted to become an energy source of the future, but it's now only going to be about 2 to 3% of the energy by 2050. The one big issue that's being overlooked is the amount of water that we're going to need, and they feel that we're going to be 30% lacking for the green future. Challenges 4 and 5. Source, oh, I've done it again, sorry. Can you get rid of that? Thank you. Sourcing carbon is a big one, or green carbon. Historically, the iron's been produced using renewables, but the 20th century saw an influx of electricity and coal and became a problem for deforestation. Energy became 20% of the OPEX, so we forced us to minimize our energy usage, but we've still got a fairly high amount of gigajoules going in. As you can see, blast furnaces, 18.8, arc furnaces are 4.3, and DRI plants are at 16. Biomass use varies significantly depending on the world location. And this is a chart at the top. Surprisingly enough, United States is the second largest biomass user. I was quite surprised when I found that. But the cost of processing basically reduces the world opportunities of use. And the question becomes, is there enough sustainable biomass close enough to the use points to match the use rates and be viable for the future? Blast furnace coke replacement is limited because of the bed support, although people are looking into it. Kobe Steel holds the record at 239 kilograms per ton of hot metal. The arc furnace carbon replacement, until recently, has been inefficient. It's averaged about 50%, and I'm talking in terms of the energy release when carbon combusts. Recently, there's been some test work done at Nucor that's showing a potential injection of carbon that can be as high as 98% for both generic carbon injection and also for the green carbon. And tests are going on through that. The other big issue is sourcing scrap of the right grade and making sure that it is the right grade if we're going to make arc furnace steel. The lowest emissions, as you can see on this chart here, is the scrap EAF renewable energy, or if you go one step further, the hybrid that's 100% hydrogen, which is going to be a problem moving forward. Most of the product quality issues trace back to the melt shop and the quality issues with scrap predominantly. The prime is dwindling, as you can see from the bottom here. This is the obsolete scrap. There's going to be a lot more of that coming to the fore because China's about to dump 40 to 500 million tons to the market. We really need to be able to sell scrap to the exacting quality standards that we do for iron ore, for example, which we don't currently. Six is the zero carbon hydrogen DRI in the EAF. When I first joined Midrex, we persuaded them to put more carbon in the DRI because it was more efficient, and the in situ carbon, like the pig iron, was much more beneficial to the electric arc furnace. And now we're going the opposite direction. With 100% hydrogen, we will have zero carbon DRI. As you can see from the right here, the kilowatts electrical are only 55%. 23% is coming from carbon oxidation. So that's one issue. The other issue is you take the carbon out of that and it becomes less efficient with injection, technically. Then you're going to have less foamy slag. You're going to have less stirring and degassing of the melt. And you're going to have, excuse me, a reduction in the heat transfer, which it promotes with the stirring. You're going to lose productivity. And the carbon in the DRI also reduces the FeO of the gangue that's in the DRI before it contributes to the actual process. So that's going to be another issue. With 0% carbon or inefficient carbon, you're going to reduce your chemical energy, the foamy slag and all its benefits. You're going to have increased cost and productivity because of the extra gangue that you're going to have to deal with in the furnace. You're going to have more power. You're going to have longer meltdown times. And there's going to have more electrode and refractory wear. And probably going to need twice the biochar to do the job. There's lower yield. I mean, you can read all of these. They're also going to have to redesign the electric arc furnace because in order to do what slag's currently doing, you're going to have to double the volume. So you're going to have to deepen the furnace to allow the reactions to occur, and you're going to have to put mechanical stirring into the furnace too, which is going to be another issue to take care of. And this is all going to be compounded by the fact that there's no DRI or less DRI grade ore. There's a chart on the right-hand side that showed from, this is from ArcelorMittal AIST a few years ago. And it said for every 1% of carbon that's in the DRI, they get up to 1.5% increase in productivity, up to 1.5 kilograms per ton of steel reduction in the electrode wear, 25 kilowatt hours per ton reduction up to, and a 1% yield increase. 7 is sourcing the DRI grade ore. Currently is about 3 to 4% of the ore mined in the world is DRI grade. By that I mean DRI grade that can be put through the DRI plant and then put to an EAF. The DRI plant can pretty much handle anything you throw at it, but it's the product going to the DRI plant afterwards that's the problem, from the DRI to the EAF. So the other issue is that the quality is also deteriorating. The iron has gone from 63.9 to 61.9. Silica and alumina has gone up by almost 2%, and the phosphorus has gone up by 0.02%. Upgrading of most of the ore, 35% is coming out of Australia. Upgrading that Pilbara ore is an issue, and they're doing a lot of work to find a way around it or find ways to do so. So the suggestion now is that they redirect through the new smelter, electric smelting furnace potentially. And then that product going either liquid to the EAF or pig onto the BOF using the current brownfield potential infrastructure, which would be cheaper, of course. There's also new technology being developed for new low-grade ore processing. There's an example of Electra here. It's taking iron from ores that are 30 to 35%. There's Calix. I'll go into that in a little bit more detail a little bit further on. And Swinburne University and CIRO have come up with this highly reducible fluxed lime magnetite pellet, which cuts out some of the processes, as you can see here. The magnetite basically comes through to the blast furnace, only going through 3 steps between it and the blast furnace. 8th challenge is the CCU's carbon capture and utility use and storage. It's substantially below net zero. The chart on the right here came from the IEA org data and statistics, and it breaks down all the different types of plants that it's been put onto. Technically, it can deal with our 54% hard to abate emissions. There's only 35 plants capturing currently, and the total is 45 million tons, which is only 0.12% of what's being generated. The 200 new CCU plants that have been announced would only capture another 0.6%. It's a relatively high conversion cost because you need carbon-free hydrogen to chemically stabilize the CO2 when you are capturing it, and fixation is limited. And sequestration has been shown to be challenging geographically. They're slated as the catch-all solution for everybody's problems. There was a comment that I've quoted here from Sandbag, Steel and CCUs, the decarb potential costs. It says they don't make sense economically, environmentally, or energy speaking. The effectiveness and the relevance varies widely across the applications. And the worst emissions reductions versus the alternative solutions in terms of, look for a solution for the hydrogen DRI and scrap route rather than put CCUs on a blast furnace. It may be appropriate for DRPs, direct reduction plants. Baotou Steel in China put one on 4th quarter 2024, supposedly to capture 0.5 and then up to 2 million tons a year. The other question becomes, if we capture the CO2, can we use it all. And that becomes a question of who can use it ultimately, because currently enhanced oil recovery, food and chemical are the only users. We did do a lot of work back when I was in Air Kid on using CO2 in steel mills for inerting, funnily enough. We put it in ladles in furnaces. We put it in AOD vessels, and it worked great. And I've always suggested that we should perhaps capture the CO2 and return it to the steel mill. 9 is the conversion costs. The future is uneconomical without government subsidies. There's 60 projects in the EU worth $92 billion. Dollars. Basically, DRI use and the hydrogen basically doubles and triples the cost of steel. The non-competitiveness that we have is already known. The US produces, this was 524. The USA is producing hot roll band 839, Western Europe 680. The world export number is 580, and China is down at 448. So the taxes, levying taxes to the non-compliant nations is a must. Otherwise, we're going to be even more non-competitive. Projects are faltering more by day. The final investment decision is basically negative because of the timelines. There's some projects noted there. It says Fasco is still in pre-feed. Algoma Steel's cost went up significantly. And a lot of the people in Europe now have pulled back, and they're waiting another couple of years to make final decisions. So, you know, I think we should look at the blast furnace and the BOF and look at revamping that as a cheaper solution as we move forward, potentially to the DRI EAFs. So new technology developments. I'm not going through all of the names, but basically they're looking at biomass, CCUs and CCS, hydrogen reduction and production, electricity, and upscaling some old non-steel old technologies, if you like, the submerged arc furnaces and the ESFs. The challenges from pretty much all of them are increased energy, scalability, timeliness to market, and the Chinese techno-economic advantages. And the best available technology and more ARD at the brownfield. I'm a proponent of more work at the brownfield sites as a stopgap while we move forward. And I'll go into a couple of those later. Timely solutions. This, I'm not going through the chart, but basically the Finex, they were saying in this right-hand chart here that it was only 15 years development. In actuality, when you trace the history, it's 80 plus years. And we have the same with Hysarna. It was a 38-year development of this cyclone converter over a smelt reduction furnace, and there's still work ongoing before it becomes a commercial entity. So looking at some of the new technologies, the electric smelting furnace, it's been used for non-ferrous and there's 3 ferrous applications, STI, New Zealand, and I'm forgetting the third one right now. But basically the excess lean ore and unsuitability of the resultant DRI to go straight to the EAF is making this potentially the solution for the future. We need to upscale it. Right now, it's only up to 1.1 tons for the circular, and it's 1.56 tons for the rectangular furnaces. The other issue is optimizing the power intensity and making it sustainable, renewable energy use, and looking at the electrodes that are currently carbon, of course. And but it will integrate into the brownfield infrastructure. Now, BlueScope, BHP, and Rio Tinto are in the process of doing a feasibility study of putting an ESF into the Pilbara region, which is apparently going to be fed by a DRI furnace. Rio Tinto has bio-iron, which is using microwaves for the iron reduction. Fortescue Prime Metals and voestalpine are developing the HIFOR process, and they've had a process running in pilot 1 ton an hour since 2016, and they're having it ton an hour demonstration plant will go into Linz in Austria in 2027, assuming it passed the FID in 2024. It takes fines, as do some of the other new processes. Modular DRP would be the solution moving forward. POSCO has the Hyrex process, and they're just replacing the gasifier from the original Finex process with an ESF. And they're going to have a 300,000 ton a year demonstration plant up and running by 2028. And they say commercial by 2030. Biomass net zero iron making. It's a resurgence, a little retrofit. Brazil is the largest biomass user for iron ore production. Of course, they're using 88% renewable energy and charcoal in the BOS blast furnaces. Logistics and graphical sustainability is a question. Can we match the new bioreactors designs to the supply and to the users? And the other question becomes the emissions life cycles. Is the land use for harvesting the biomass versus producing charcoal and crops, is that viable long term? And can carbon neutrality actually be achieved? The red smelt in Brazil claims that they can achieve it. They're going to use a rotary hearth furnace and a smelt reductor, and that will replace the SAF. Ferrosilva is going to put in a DRI plant, and they think that they will have a 0.8, 0.9 ton CO2 sink per ton of steel. They're going to use syngas from the forestry and the agricultural waste, and they'll put biochar to the steel mill. They'll have CCUs integrated into the plant, and they think they'll be able to ship the CO2 to create fossil-free ship fuel, ultimately in biomethanol. They're in the middle of a pre-study, and they've been given money from the government to do that. And they're designing a 50,000 ton a year DRI plant, and it's going to go into Ovako in Sweden. Solid DRI processes. Calix, I mentioned earlier, they have a flash reduction of fines. It's now actually 3.5 years since inception. They're processing fines and waste materials. What they basically have is two concentric tubes. They don't use hydrogen for anything but reduction of the ore, and they heat with renewable energy outside the actual reactor. They believe that they can get stoichiometric hydrogen use, which will be a plus. And there's a design here on the right showing the zesty iron going into a zesty steel making plant where they're going to use their Lilac zero CO2 lime production unit to feed into the steel mill too. They are about to be funded for a 30,000 ton a year demonstration plant. Solid DRI processes, I was surprised to see that the DRI shafts are only being shown as TRL 6 to 8. And I'm assuming that's because of the hybrid hydrogen DRI EAF. The open questions are still carbon in the DRI or not, and lean ore processing moving forward. The hybrid plant, they've proven that they can produce 1 ton an hour of DRI, excuse me. And they've proven this, they've proven this 100 cubic meter lined rock storage, which they require for the hydrogen, but they're going to have to put in 120,000 cubic meters when they move to this new 1.3 million ton a year plant that they're putting in, because they're going to need 100 gigawatt hours for a 3-day operational backup. That's going to be put into Norway. Hydrogen rotary kiln is going to run on solar and wind, renewable energy. There's a 0.5 ton an hour high iron DRI pilot in Lingen in Germany. That's run on 14 megawatts of renewable energy. And they're going to have a joint venture with Hyron Steel in Namibia. And there'll be a 15,000 ton a year DRI plant to start with 20 megawatts of solar. That should have started last year, but I don't believe it started yet. And there's a 2 million ton DRI plant going to be produced ultimately with 18 megawatts of wind and 440 megawatts of solar. Electrolytic iron making, electrowind, at either the high temperatures of 1500 degrees or low temperatures around about 110. Basically a reduction reaction where iron's coming off at the cathode and oxygen at the anode, and the ore's own oxide ions are the reducing agents. Higher energy efficient, renewable energy direct contact. And high temperature one basically dissolves ore in a molten electrolyte, giving liquid iron faster kinetics. Higher capex, higher opex. ArcelorMittal looked at the Mideo Olcos back up to 2012. I don't know what status that is right now. There's a low temperature one is a solid process, which has got slower reactions, obviously, but it's got lower energy use and it's a lower capex and opex. And the ArcelorMittal Ciderwin is a demonstration plant at 110 degrees. Excuse me. Boston Metals is the United States example. It's a high temperature batch MOE. Can process a wide range of ores, but it's limited in terms of productivity per cell due to current density and Faraday's law. The critical factors that they have to achieve is recarburizing, anode longevity, excuse me, and the type of anode, and actually scaling it up. There was an article last week that said they finally produced a ton of steel through that process. It took a couple of weeks to do so. The one other big issue is that last I heard they were running at 20 volts and they need to be down at 5 volts. But there is a big compatibility with brownfield. However, the example on the right-hand side here, it's granted a plant in China and it's not steel. This is the aluminum plant, but they're saying that they'll need 300 to 400 cells to produce 500,000 tons of steel. And I can't really see anybody putting 4,000 cells into a plant that makes 4 million tons a year, personally. Maybe. They've had a lot of DOE funding. They've got a commercial mine waste processing plant that began last year in Brazil. And they believe they'll have a production for steel up and running by next year. Electrolytic iron making, Electra is Bill Gates and Amazon backed. They've been going for about 3.5 years now. It's a low temperature process. They're taking low grade ores of below 55% iron up to 99% and more. It's electrochemical and hydrometallurgical process. They're creating 1 square meter, but we don't know how thick a plate with virtually no tramp elements in it. And they're going to charge the plates to EAFs. It's a modular design, and they think they can reduce the CO2 by 90%. There's all-cost offshoots, the Ciderwin I just mentioned, 87% reduction in CO2, 31% direct energy use reduction. Alcowin, which is a low-temperature direct alkaline electrolysis, and then the other one is alcolysis, which is a high-temperature electrolysis like Boston Metals. Plasma iron making is coming back again. It's a hydrogen plasma arc, and it's electrode to ore in a conventional EAF basically this time. Very energetic exothermic hydrogen species, which overcomes the endothermic hydrogen problems. They have enhanced kinetics and energy savings, they're saying, lower reaction temperature. There's a pre-pilot demo in Leuven, University of Leuven, with Voestalpine collaborating with them. And they're calling it SuSteel. Historically, it's been very overpriced and it failed back in the 80s and 90s. They needed to basically find lower capex and opex. They need to find a refractory life protection or find a new refractory that will compensate and they make it continuous production, basically. There are some examples. There's the hydrogen plasma red, which is an EU R&D project, 100 kilogram scale. And if that works, they're going to put it straight to a DC current EAF. There's a waste alumina bauxite running at 180,000, million tons a year. Excuse me, that's turning into iron making feedstock. And I already talked about this plasmolysis jet loop, which is stripping ammonia from wastewater and manure. I'm sorry, I've done it again. I can't chew gum and walk at the same time, sorry. So we look at the brownfield decarbonization opportunities. They're anticipating that we'll still need 50% ore-based steelmaking by 2050. The greatest CO2 reduction potential exists with the blast furnaces, and best available technology could reduce this by 25%. Improved measurements in the mill. Blast furnace pellets versus sinter is well known. That reduces the CO2 by 85%. Intensifying metallics use in both the blast furnace and the BOF. I'll get to that in a minute. The IIMA out of the UK is saying that you can gain 8 tons an hour and 7% coke reduction for every 10% extra metallization that you put into the blast furnace. And back in the 80s, US Steel was doing this. Biochar substitution for coal and PCI, that's already being done. Hydrogen or natural gas twin injection, it's been shown to reduce CO2 by 9% versus non-injection. And Hatch has said that pulverized coal injection plus 35 kilograms of hydrogen, but at 900 degrees C, will give you a 20% reduction in the CO2, 35% extra energy to the mill, and 100 kilograms of coke reduction, but it's going to cost a lot of money. If you add to that top gas recycling and CCUs, you'll get about 80% reduction in your CO2, and that'll bring the CO2 down to about 0.4 tons of CO2 per ton of liquid steel. Then there's the Japanese Course 50 program. They've already proven 30% reduction with what they're doing with the hydrogen, coke oven gas, and CCUs, but that's only a 12 cubic meter diameter furnace. The aim for them is to bring this down to 50% reduction using blast furnace with DRI and hydrogen. I've already mentioned Kobe Steel's 239 kilograms of coke. They did that with 20% lump, 80% self-flux dolomitic pellets, and PCI at 220 kilograms per ton of hot metal. Utility H2 Gen, they're creating hydrogen from water, but they're using electrochemical energy in the gases, and they're basically taking process gas, off gas, blast furnace gas, as they did in Cleveland, Nanticoke. And they're taking that off and using that to basically transfer energy through to the electrode and taking hydrogen off. So they're basically doing electrolysis, but they're using the blast furnace gases as the thermal entity, not energy. They're saying that for plants less than 20 tons of hydrogen per day, it's going to be less than $5 per kilogram, which is great because right now, to buy hydrogen, you're looking at $4.5 to $13 per kilogram, depending on where you are in the world. If you put in 20 tons of hydrogen or more, it's going to drop down below 3 kilograms. And there's a commercial plant going in the near future, but offshore at 3 tons of hydrogen a day. BOF, increased scrap use in the BOF. At one point, we were actually testing 40 to 50% in the BOF. Current word average is about 17%, and I believe here in the US we're between 20 and 25%. There's a program that was built by Swinburne University using plant data there, and the graphs show that data here. 35% scrap charge into the BOF drops your heat loss down to like 0.9%. If you go down the other direction, of course, you're going to have a much higher heat loss, up to 6 to 7%. If you increase the post-combustion ratio from 10 to 30%, which is this one down here, then you're going to increase the scrap from 22 to 28%, but you'll decrease your global warming potential by 10%. Hydrogen, HBI in the BOF, of course, is going to give you a bigger cooling intensity and productivity versus scrap, and that's shown in the graphs at the bottom. And again, the blast furnace off-gas use for hydrogen generation, and they can actually intensify the CO2 to 75%. Electric arc furnace brownfield. The key here is, of course, renewable energy. It would take, as you can see on the right here, it will take the scrap from 0.38 down to about 0.18 if you've got the renewable energy on the furnace. We need to beneficiate and maximize the scrap use, because as you use DRI, you're increasing your CO2, obviously, unless it's 100% hydrogen use. If you shred in-house, excuse me, you can intensify the density of the scrap that's going into the furnace, make it smaller, make it melt faster. You can also benefit from the profit of selling off the shredder residue, which is usually non-ferrous and quite valuable. You also need continuous analysis in the plant, which is still being developed, so that you can know what's going into the furnace in real time. The other options are to develop residual insensitive steel grades, which is being done, I know, in England, but I'm assuming it's being done here too. Or find a way of removing the residuals from the scrap, which is a problem. You can reheat the post-combustion or combustion air that's going into the furnace, and you can halve the kilowatts and pretty much take off 16 minutes from the meltdown time. We need to develop green carbon and consumables for the furnace. Hydrogen substitution, partially or completely, for the natural gas burners when it's cheap enough to use it. But also use tools like the value in use or off-gas analysis to allow you to present the lowest cost liquid steel of the right quality. And it's a great tool for basically minimizing your operational losses. And there's some this graph on the right-hand side here just shows you, if you want to make auto steel, you basically got a very low residual, and you have to be using huge amounts of HBI, DRI, pig iron, or prime scrap to do it. Industry status. This is a great tool you can play with, this global tracker. These are all of the development projects in the world as of when I wrote this. It's showing 1,163 steel mills, iron and steel, and it breaks it down, as you can see, whether it's electric or integrated BF or integrated DRI, not going through it all. The numbers on the dots and circles all represent the colors on the right here are the specific colors, excuse me, on the graph. Where you've got something like 19 in the circle, it's 19 plants in there. You can explode the plants out, and then it will highlight what kind of plants they are, how many there are of each type. And you can go in, did I lose my bottom one here? I went into the one down here in South Africa, and then you can hone in on each individual plant, get data about each single plant. And you can even drill further down into that to get data on each individual plant. But it is a great tool. I actually had a demonstration going through each different angle, but it's too much to put into here. This is just a summary of the operating, all of them, then the operating, the announced, and those under construction. Those are the ones that we're looking at. But basically, the announced, DRI and blast furnace now are almost equivalent, whereas 2 years ago, there were virtually no blast furnace, new blast furnaces being announced. And if you go down to the iron making down here, the iron making is catching up, but the DRI is still ahead in this particular instance. This graph on the right is just Prime Metals forecasting what it'll look like in terms of who's building what, and what's still a lot of scrap in the EAF here at the blast furnace. This is the scrap. International solutions, people are looking now at decoupling. China's got very young blast furnaces. It's unlikely that they're going to give them up quickly, although they are putting in a lot of electric furnaces. They put in an order last year for 10, which is quite surprising. India has got a low tons of scrap availability, so they have to rely upon DRI. And in Europe, of course, this all started because they really don't have any natural gas unless they buy it from Russia or have it sent in from us. We were sending a lot of liquid natural gas over at one point. Renewable energy sources vary by location, of course. China's got the largest renewable energy transition going on at the moment. MENA has got a lot of solar going in, and they've just put in they're putting in a Midrex Flex run on solar, and I believe that the Tosyali is already running theirs on solar. Australia, of course, got lots of ore, renewable energy, and investment potential, and there's a lot of foreign companies looking at investing in Australia because of that. There's a lot of international alliances already ongoing. I'm not going to go through them all because of time constraints, I believe. How are we doing? The CCU scale-up is apparently vastly overestimated for the Chinese, the Indonesian, and the South Korean deployment, which is what's really needed to clean up, because most of the pollution is coming from that side of the world. Just showing you where China, the black dots on this graph around Africa, are where China's expanding into Africa currently. There's some commentary here on the regions and the market strengths and the key challenges that are ongoing. I think I've covered a lot of it. Common challenges to every one of the new installations and the cost thereof, whether they should go with green energy, green hydrogen, and EAFs or not. It says there's no new blast furnaces going in, and they're phasing out the old ones. If you look at that global energy tracker that I've just shown you, there are a lot of blast furnaces going in around the world currently, brand new ones. So there's going to be 20, 25 years before they're down. These are some of the development projects in Australia. I'm not going to go through them all, but there are quite a few ongoing. They've got ESFs going in. Liberty Weil has been taken over by the government, and they're debating what future will be, whether it's blast furnaces or ESFs or high smelt, maybe. I've mentioned Rio Tinto's bio iron and Fortescue's Christmas Creek. There's a new steel mill, Collie Steel Mill, going in. The government's putting out $780 to $1 billion of Australian dollars to invest in green future. These are committed most of them still are, I believe, committed installations from Europe. If anybody's interested, I have a new chart that just came out that shows the map of Europe and numbers all of the plants that are in the original 60 and where their status is, and they've got them all highlighted now in various stages in their final green steel or actual installation dates on them, and they're quite a long way out, 2 to 5 years, if not 10. So in summary, the scale of progress and investment falls way short of the 1.5 degrees C global warming that we are trying to achieve, but I don't think we're going to get there at the timeline that they're expecting. Hydrogen DRI EAF steelmaking is technically viable, but it's challenged by the build rates and the availability of all the green consumables and the conversion costs. And the conversion costs have turned out to be one of the most difficult things to come to terms with. We've got a catch-22. We've got the need for guaranteed low cost of low carbon energy and hydrogen, and the people who are making them need to have commitment to move forward. There's a potential for decoupling the iron and steel making around the world, put the ore with the iron making and ship the DRI or the HBI or the pig iron to the steel makers. In the meantime, we need the black steel taxes for non-compliant nations, and they need to be fairly substantial. The best available technology and continued R&D needs to go on with the brownfield sites. But I truly think the green steel revolution has spawned a lot of opportunity for this industry. We really need to be able to put innovation to market quicker than we have in the past. We need to make sure that we can use CCUs as a fix for the steel industry. And the hydrogen production needs to be far more efficient and less costly for us to be using it in the future. But it is a fantastic industry to move into. Truly, I can tell you some really interesting stories, but maybe Professor Chen doesn't want me to. And I probably would have been thrown out of the industry years ago if I did what I did then now, because of safety. If anybody wants to know about my career history, it's out there on the AIME as a oral history, some of the crazy things I have done. Anyway, it's a major career opportunity for all of you, so please consider the steel industry moving forward, and I thank you.